Hi, this is Ms. Fitzmaurice, and this video is an explanation of the free response problem on Unit 4, page 17. Okay, so before you watch this video, of course, I want you to try this problem. If you're really stuck, just go through and, write in part A, I think I should use this. In part B, I think I should use this. But I really wanted you to give this a try. And then what I want you to do is watch the video and correct yourself, okay? All of our packets have a little sidebar on the side, and what I want you to do is put questions or comments in this sidebar, or just keep track of what did you miss and why. Okay, so now that you've taken the time to try this problem, we're going to go over it together. Alright, so here's the basic setup. We have a car and it is moving to the right. There's a motion sensor tracking its motion, and a force sensor records the force as it impacts the force sensor when it gets to the other side. Okay, so these two things, they're probably hooked up to a LabQuest and then hooked up to Logger Pro, and they make these graphs below. Okay, in part A, it says determine the cart's average acceleration between t equals 0.33 and t equals 0.37 seconds. Alright, so there are two possible ways to go with this. One possible route is you could use F is equal to ma, okay, and you could maybe somehow use the force graph. The other way, and this is going to be easier, is that average acceleration is change in velocity over change in time. And we can actually just read the change in velocity over the change in time straight off of this graph. Okay, so in part A, you want to use this. Alright, in part B, we want to know the magnitude of the cart's momentum. So think about impulse, which is defined as change in momentum. Now we also know that impulse has another equation, so delta P is also equal to F times T. What this tells you is that change in momentum will be equal to, because these are multiplied together, the area of a force time graph. Okay, so we're going to go ahead and we're going to find an area in part B. In part C, we want to find the mass of the cart. Okay, so what we can use for that, we know in impulse that m delta v is equal to F times T. Okay, we can look at one graph, our first graph, to find delta V. So we have delta V. We have the average force, or we can at least find the average force, and we have time. What we can do is remember that this average force is equal to the area under the FT graph. Okay. Finally, in part D, we want to find the energy lost in the collision. So we're really looking for a change in kinetic energy. Okay, so we have 1/2 mv squared minus 1/2 mv naught squared. Okay, so if you have not already tried the problem because you weren't sure what to do, I want you to take these steps and go ahead and try the problem. Alright, so in part A, remember we're using A average is equal to change in velocity over change in time. And we want it between 0.33 seconds and 0.37 seconds. Okay, so that automatically tells us the change in time. 0.37 is the final minus 0.33. The change in velocity, we have to read those directly off of the velocity graph. So I'm going to say that it was about 2.2 before, okay, that's our initial, and it dropped down to about negative 0.18, okay, so negative 0.18, and this should read 0.22, not 2.2, sorry. Okay, so remember, it's final minus initial. So we have negative 0.18 minus 0.22. Okay, and we end up with about negative 10 meters per second squared. Okay, and remember in part B, what we have to do is we have to find the area. So delta P will be the area under the FT graph, and that's the whole entire area that we care about. And so what I've done is I've broken that area up into 3 sections, and I'm going to find the individual areas and add them up. So I have 1, 2, 3, and area 4. Okay, and just looking at it symmetrically, I can tell that area 1 and area 4 will be the same number, so I'm only going to calculate 1. Alright, so what we need to do is we need to calculate the area for each one of these regions. Okay, as we can see, region 1 is a triangle, so it will be 1/2 the base times the height. And in this case, the base is 0.01 seconds, and the height is 10 newtons. Okay, so we have 1/2 times 0.01 times 10, and what that gets us is 0.05. Okay, and it's in the units of momentum, kilograms times meters per second. In area 2, okay, this is a rectangle, so it's going to be base times height. The base is 0.02, and the height is again 10 newtons, so we have 0.2 kilograms times meters per second. Of course, region 3 is also a triangle, so we can calculate that using 1/2 base times height. Okay, and that's, again, the base is 0.02. This time the height from 10 to 40 is 30 newtons. And when we calculate that, we end up with 0.3 kilograms times meters per second. And of course, region 4 is the same as region 1, so that's 0.05 kilograms times meters per second. Okay, to calculate the total change in momentum, we have to add all of these up. So it's 0.05 plus 0.05 plus 0.2 plus 0.3, and that ends up being 0.6 kilograms times meters per second. Okay, in part C, we want the mass of the cart. And of course, we're going to use delta P is equal to J, and that J is equal to M delta V. Okay, so we know that from the last one, we know that the change in momentum is going to be 0.6. I'm going to argue that it's actually negative 0.6 because we see the momentum decrease. So we have negative 0.6 is equal to this mass we want to know times change in velocity. Okay, to get the change in velocity, we can read that straight off the graph. So we know that the velocity went from 0.22, so it's final minus initial. So the initial is 0.22, and the final is about negative 0.18. Okay, so we can solve pretty easily for the mass. And when we do that, we end up with about a mass of 0.67 kg. In part D, it says determine the energy loss in the collision between when it hit the force sensor, or before it hit the force sensor and afterwards. Okay, so remember that in general, kinetic energy is equal to 1/2 mv squared. We want the change in energy, so we have final minus initial, so delta K is equal to the final kinetic energy minus the initial kinetic energy. So that ends up being 1/2, and we can use the mass, 0.67 times the final, which was 0.22 squared. Actually, that was the initial. So the final was negative 0.18. So we have negative 0.18 squared minus 1/2 times the mass, 0.67 times 0.22 squared. Okay, and when we do that calculation, we end up with about negative 5.3 times 10 to the negative 3. And don't forget, this is in joules. So our change in kinetic energy, or our change in energy, was negative 5.3 times 10 to the minus 3 joules. Or millijoules, if you want, because 10 to the negative 3 is milli.